All right, this is lecture 5, part 1. We're going to do this lecture a little bit differently because I didn't quite finish chapter 14.3 last time. So I'm going to have a separate section where I finish chapter 14.3, and then I'll separate that from when I start chapter 14.4. All right, so the reading for today is chapter 14.4. It's on the chain rule. The problems for today are at the end of chapter 14.3, 41, 45, and 55, and then at the end of chapter 14.4, 1, 5, 41, and 43. This is the warm-up problem. It's hard. It's hard for two reasons. First, I haven't told you how to deal with multiple partial derivatives, but really that's pretty straightforward. So the way that so y here is a function of x and t. And so if I want to take the second partial derivative with respect to t, I just take the partial derivative with respect to t, which you've done and know how to do. And then whatever I get, I just do that again. I take the partial derivative of my answer with respect to t. All right, so that's how multiple partial derivatives work. And I'll discuss that in the section about where I finish up chapter 14.3. So if you want to wait on this warm-up problem until you see that part of the lecture, feel free to do that. All right. The other reason that it's hard is that you really have to have mastered the chain rule for a function of one variable in order to do this problem. And that's actually part of the reason why I assigned it, because we're going to be talking about the chain rule, and I really need you to remember the chain rule for functions of one variable. All right. The other reason that I assigned it is that this equation here is called the wave equation, and it governs the shape of a plucked string. So in fact, the example that we did last lecture where we looked at a plucked string, it's governed by this equation. And the mathematical model that I used was a modified version of this equation. All right, and what you're going to do is you're going to show that this is a solution to this equation. And what's interesting is that it's just a form, right? So I haven't told you what y of whatever is, right? And if you think about this, imagine at time t equals 0. This is just some function y of x, whatever that looks like. And as time goes on, what this does is whatever it was at time t equals 0, whatever shape it was, just propagates to the left, right? So that's what this is, and what you'll see is that this is a solution to to the wave equation. So when I take my string, excuse me, and I pluck it, whatever that initial deformation is, it propagates to the right. Now, things get a little bit more complicated because we have to worry about the fact that I'm holding the ends of the string. And we also, when I simulated it, I had to worry about the fact that there's a little bit of damping, so the string stops vibrating after a few seconds. So I took that into account in the model, but this is sort of the basic idea behind the model. All right, and if you look really, really carefully in those movies I made, particularly in the experimental movie, if you go through almost frame by frame, you can see this initial perturbation, this initial pluck, propagate to the right in that movie. All right, let me erase this, and then I'll finish up chapter. Sorry, I'll erase this, and then I'll remind you what we talked about last time. All right, hold on a second. Okay, so last lecture we talked about partial derivatives, and what we found is that for a function of two variables, but the idea is the same for a function of 4, 5, or however many variables. The partial derivative of f with respect to x, which we write this way with these sort of weird squiggly looking d's. So the partial derivative of f with respect to x is it looks just like just like the limit definition of derivative that for a function of one variable, okay, so just like the limit definition of derivative for a function of one variable, holding the other variable, or if this were a function of 4, 5, or 20 variables, holding all of the other variables constant. All right? So let me write that down. So this looks like the one variable definition of derivative with y constant. And indeed, that's how we calculate it. We take the derivative of f of xy, and we treat y as a constant, and then we treat x as if it's the only variable that we know, and we do all of the usual derivative things to calculate what that is. All right, and then the same thing is true for the partial with respect to y, except instead of delta x, now we have delta y, and I put that increment over here. And it looks like again, looks like the one variable definition of derivative, but in that case, x would be a constant. All right, let me erase. And then what I'm gonna try to do now is try to give you a little bit more of an intuitive definition of what this means. Okay. Now, supposing, here, I'm going to draw a plot. Here's x and here's y. And I'm just going to draw a generic contour plot. So I'm just going to draw a series of level lines. All right, so the idea is that z is a constant along each one of these lines. Maybe this is, it doesn't really matter, but let's say that this is z is equal to 30. This is z is equal to 20, and this is z is equal to 10, say. Doesn't really matter. All right. Now imagine that I'm standing here. Imagine that imagine that I'm standing at this point. Well, you could imagine that when I stand at this point, and maybe I'm facing upwards along the y-axis, then the partial derivative, so these are all lines of course, z is equal to f of x, y. Okay, so these are all lines of z is equal to f of x, y. Then df dx at this point is the slope in this direction. So if I'm standing at this point, I'm facing in the y direction, then the partial derivative of f with respect to x at that point is the steepness to my right. Similarly, here's z is equal to 10. The partial derivative of f with respect to y is the slope in front of me. And so when I say df dx is the slope in this direction, if I were facing in the positive y direction, it would be to my right. Okay? Why does that make sense? Well, one way to think about it, there's two ways that I want you to think about it. the first way is imagine that I'm really standing here. Imagine this is really a topographical map and I'm really standing here. Then df/dx is telling me if I take a little step to my right, how much does the height increase or decrease? That's what df/dx says. It takes whatever that height increase or decrease is divided by my step length, and it tells me that's this value, that's df/dx. df/dy is me taking a little step forward and doing the same thing. How does the height change? Does it increase? Okay, how much does it increase relative to the size of the step I'm taking? And that's what df/dy is. How much does it decrease relative to the step I'm taking? That's what df/dy is. All right? So that's one way to think about it. Another way to think about it is imagine that I take a slice here. Imagine I'm taking a slice through this. So let me draw that. Here's this slice through my function. And if I take a slice here, I'm fixing y is equal to a constant, then I'm going to have x on one axis and z on the other. If I try to draw this, it looks like I have a curve that looks something like this. Something like that, where this height would be, right, it looks like right here as it crosses here, that's 20. This is a little bit bigger, and then it drops, all right? And so we're over here, here's 20, here's 10. So we're not quite at 10, so maybe we're right here, okay? Well, what's df/dx? df/dx is this slope. Okay, so this is one of the reasons that I wanted you to think about taking slices through this function, is that df/dx is telling me if I take a slice here, what's the slope at this point I'm standing, right? It's like I'm treating my function of two variables as a function of one variable on that slice, holding y constant. Same thing here, just the other way, it's just the same thing, except now I'm taking a slice in the other direction. Now I'm holding x constant. All right? Okay. So I'm going to leave it at that. And we're going to be thinking about this kind of picture, and we're going to be trying to connect this kind of picture to our calculations in discussion section tomorrow. All right? Okay. So that's the end of the review. What I'm going to do now is we're going to take a break, and I'm going to start talking about the rest of chapter 14.3. And then I'll post the solution to the warm-up problem. You can watch those in whatever order you want, but if you don't feel super comfortable about taking multiple partial derivatives, watch me finish up the material in chapter 14.3. All right, see you in a sec.